Good morning students. Today we are going to discuss a few important topic from the chapter 4, that is your moving charges and magnetism. These topics are very important for your exam. Now the topic which we are going to discuss is your the first topic, toroid. Now what is toroid? Let me read out first of all. A toroid is a hollow circular ring of finite thickness on which a large number of turns of an insulated wire are closely wound. Now basically a toroid is a circular solenoid, you can say, circular closed solenoid. Now in the figure this is your core, and over the core there are windings, and current I is flowing through the windings. Now this is another figure because we are interested in defining the magnetic field inside the toroid. So that's why we have drawn figure 2. So this is the outer edge and this is the inner edge. So what we have considered, a dotted circle of radius r well inside the toroid. Now the magnetic field, and if you consider a small section dl, then both are in same direction. Now if we trying to define closed integral b vector dot dl vector, then b dl cos 0 degree, and b comes out dl. So dl is nothing but is your circumference, that is your 2 pi r. Now if we apply Ampere's circuital law, b dl closed integral dot product equal to mu naught times the current enclosed by the closed path. So the radius r smaller encloses lots of windings, and if n is the small n is the number of turns per unit length, then the length of radius r is your 2 pi r. So 2 pi r into n gives you total number of turns, and on each turn there is a current I. So mu naught times the current enclosed by the circular loop, so that is your Ampere's circuital law. So b vector dot dl vector mu naught n 2 pi r I. So from 1 and 2 you can simplify b 2 pi r mu naught n 2 pi r I. So 2 pi r goes up, so you do have b equal to mu naught n I. So this expression is same as that of the magnetic field inside a solenoid. So sometime in exam it is asked to define the magnetic field inside toroid or magnetic field inside the solenoid, and in that case we have to draw this two figure 1 and figure 2. Now the next topic which we are going to define is your forces between two infinite long straight wire. Now two wires we have considered, and through the wire current I1 and I2 is flowing. So current I1 produces magnetic field near current carrying wire I2, that is we have defined B1 vector, and you can define the direction by using right hand thumb rule, considering thumb as your direction of current, and the curved finger gives the direction of the magnetic field. So another way, the another magnetic field basically B2 is also due to the current I2, and B2 is near the current carrying wire I1. Now B1 and I2, B1 is already the magnetic field due to the current I1, and I2 has its current, so definitely it has its magnetic field. So interaction between the two magnetic field, there is a force. Similarly, in case of current I1, there is a magnetic field, and already there is an existing magnetic field B2 due to the current I2. So there is an interaction, and as a result there is a force. So B2 vector, what we have written here, magnetic field perpendicular out of the plane. So this is the symbol, circle with dot, this is out of the plane, circle with cross, this is perpendicular into the plane. So if you apply Fleming's left hand rule, you will see that F1 and F2 are in opposite direction within the interior region of the wires carrying current I1 and I2. So F1 and F2 are basically force per unit length. So from Biot-Savart law, if we define magnetic field B1 due to the current I1, then it should be your mu naught I1 2 pi d, and similarly B2 is your mu naught I2 2 pi d. This one already we have discussed in our previous class, magnetic field due to infinite long wire using Biot-Savart law. Now again there is an expression that is your force F1. F1 is your B2 I1 and F2 is your B1 I2. So you have to substitute B2 and B1. So if you substitute B2 and B1, then F1 B2 value is your mu naught I2 by 2 pi d into I1, and F2 equal to mu naught I1 2 pi d I2. That is your B1 value we have substituted. So both expressions are identical. So these expressions are very important for numerical as well as for derivation. Now the next topic which we are going to discuss is your torque on current loop in magnetic field. So there is a current carrying rectangular loop is there, and the direction of current already we have specified. Now the magnetic field is already there. So again you have to apply Fleming's left hand rule. Now if you apply Fleming's left hand rule, you will see the direction of force F1 as well as direction of force F2 is along that direction, which is specified in the figure. Now F1 acts throughout the length L, and F2 also acts throughout the length L. So in figure 2 you see we have considered the top edge of the rectangular loop, that is your QR, and magnetic field is there. So there is a normal to that loop that gives the direction of the rectangular loop or the direction of the area, and that one makes an angle theta with the magnetic field. Now if you see simple geometry, you will see and in the right angle triangle, the two angles are theta. Now the force, if you see the expression number 1, F1 F2 are identical, that is your BIL, as we have defined in our previous classes. Now torque is nothing but is your force into perpendicular distance between the line of action of two force, magnitude of either force, that is your F1 F2, and perpendicular distance between the two force is your OR, that is the perpendicular distance of the line of action of the two force, that is your OR. Now that part is your B by 2, you can whole B. So in downward, if you consider OR is nothing but is your B sin theta. So F1 is your BIL, B sin theta. So BIL, B sin theta. So LB is nothing but the area of the loop, length into breadth. So BIA sin theta. Now if the loop is of n turns, then you simply have to multiply by small n, that is your tau equal to NBIA sin theta. Now for a special case, you can consider if theta is pi by 2, then tau equal to NBIA, that is the maximum one, and if theta equal to 0, then tau is 0. So these are very important topic, and you must have to understand. Once you understand, it becomes very clear. But out of these 3 topics which we have discussed today, definitely one topic you will get in your board exam, and these are very important: torque on current loop in magnetic field, force between two infinite long straight wire, and another one is your toroid. So please go through and find out your difficulties, and make your habit to ask question during the class. Once you study, then definitely you can ask question, but if you don't study, then you are not supposed to ask anything. So please do study and put your doubts during the class. So this is all about. Thank you.